Hello, this video will be about a method called partial fractions. The idea here is that we are going to learn a clever way of breaking up something into multiple fractions in the hopes that an integral that seems impossible actually is possible. And we're going to be focusing on rational functions. Right? I will remind you a rational function means a polynomial function divided by another polynomial function. And there are a lot of rational functions we already know how to integrate. So I have 5 examples here. Hit pause for a moment and ask yourself if you know how to integrate these. Maybe you don't need to get to the final answer, but I will say theoretically you should be able to do all of these integrals and maybe do a few of them. At the very least, recognize which ones you remember how to do. All right, so I hope you have done that. So this first one, for example, right, theoretically it's u substitution, but basically we just have 1 over something linear. If you make a u substitution, it's like natural log. So this would be natural log of absolute value of x minus 4. If we took the derivative of that, we just get 1 over x minus 4, and then we multiply that by 7. So technically u substitution, but we can kind of just do that in our head. And this one here is the same, except if I had natural log of absolute value of 3x minus 4, by the chain rule, a 3 would pop out, and so we would need to cancel that 3 plus c. So if our bottom is just linear, right, if it's number over linear, we can do it with natural log. Now this problem is very carefully engineered so that it is doable. Because what we might notice is that the numerator is the derivative of the denominator. So we actually have natural log of the denominator. If you took the derivative of this, you'd get 1 over that thing times its derivative, which is this. So this one very specifically works because of the very specific relationship between numerator and denominator. Right? This one, again, kind of use substitution. Oh, it's something to the negative 2 power. This is the basic pattern we have. So negative 3 times that thing to the negative 1. Right, looks like that would work. Negative 1 comes in front to cancel. Power is negative 2. Technically, we multiply by 1 by the chain rule, but that doesn't affect anything. And then over here, this one might be harder to recognize, but lurking within this is 1 over u squared plus 1. So what we actually have here is 3 times inverse tangent of x minus 5 plus c. If we did derivative of inverse tangent, we'd have 1 over this thing squared plus 1 times, again, 1 from the chain rule, but we can get away with not writing that down. So here are a bunch of rational functions that you do know how to integrate. But if you randomly make one up, my guess is you don't know how to integrate it. Right? What if we have something like this? Integral of 17x plus 1 over 3x squared minus 5x minus 2. The numerator is not a constant, so it's not as simple as those ones with just the substitution. The numerator is not the derivative of the denominator or a multiple of the derivative of the denominator. So nothing similar to what we did so far seems to work directly. All right, well, hey, let's do some algebra. Right, so for no particular reason, practice your algebra skills and simplify this addition problem of fractions. Hit pause and do it. So I will notice I have 2 fractions added together. I need to create a common denominator, right? Just like, 5th grade style, I'm adding fractions. So for the first fraction, I multiply top and bottom by x minus 2. For the second fraction, I'll multiply top and bottom by 3x plus 1. So I can combine these, and my common denominator, let's FOIL that out, 3x squared minus 5x minus 2. And then I have 2x minus 4 plus 15x plus 5. So that's 17x plus 1 over 3x squared minus 5x minus 2. right? And you'll notice that we weren't doing this randomly. This is actually what we were trying to integrate before. So what I am springing on you is it turns out that this rather exotic looking rational function is the result of adding together two much simpler rational functions, right? This is number over linear. This is number over linear. These are very simple, but when we add them together, it doesn't feel as simple anymore. But now that we know this, how could we do that integral from the previous page? Well, we could recognize that this complicated fraction is actually this reasonably nice fraction plus this reasonably nice fraction, each of which we can integrate using natural logs. So this would be natural log of absolute value of 3x plus 1 multiplied by 2/3, the 2 because we had a 2 in the numerator, the 3 to cancel the 3 from the chain rule. By similar logic, this would be 5 times natural log of x minus 2. There's a 1 from the chain rule, so we don't have to cancel it, plus c. So given that we know that these two fractions equal this fraction, we can rewrite it. But how do we know that? I fed this to you, right? This is very easy to do if someone just tells you, psst, add together these fractions and see what you get. We want to learn a way of figuring out those fractions, right? Is there a way where if I had started with this thing, somehow I could figure out what is that partial fraction decomposition? Okay, so that term, partial fraction decomposition, is when we take something complicated and we break it up into simpler fractions. Decomposition. That's not very clear at all. So I'm going to walk you through how this works. It's the kind of thing where when described in the abstract, it doesn't feel all that helpful. You are going to get good at this by doing examples, not by trying to memorize what the steps are in an abstract way. And the thing that really makes this possible is this denominator we started with factors. In a very abstract technical sense, all quadratics factor, but often to factor a quadratic, you need to introduce irrational or possibly even non-real numbers. We're going to be restricting to cases where it is a nice integer-based factorization. So you're going to have a lookout where when you're seeing these kinds of problems and you're like, oh, that denominator factors, that's actually a hint to me. So here's the idea. We're going to be looking at examples where we have a proper rational function. Remember, proper means the denominator has a smaller degree. And we're going to be assuming that the bottom has two linear factors. So the idea is either it's number over a quadratic that factors, or it's going to be something linear, degree 1 over a quadratic that factors. Right? But it needs to be of that form. The numerator needs to be simpler than the denominator. We'll talk about how to handle cases where that's not the case later on. So what we're going to do is we're just going to hope that something like what we saw before works. So some number over one factor plus some number over the other factor gives us this thing we started with. Because we're feeling like, oh, if I create a common denominator here and I create a common denominator here, that gives me this denominator I started with, and then maybe all the algebra works out. If we multiply both sides by both denominators, this is essentially what we're solving. And then there are really two different ways of solving that. One is we're going to equate coefficients. The other is we plug in numbers. But one thing I want to stress here is that we want this to be true. For functions. So the idea is we're going to get some algebraic expression on the left, and we're going to get some algebraic expression on the right, and we want them to be literally the same function. Right? We're not saying they're equal when I plug in something specific. We're saying they are the same function on both sides. They are always equal. So here's an example to watch. And I'm going to create an extra page for my work, because I'll probably need it. So right off the bat, I notice that that denominator factors. This technique really only works when we have a factorable denominator. So that's what you're going to see for these examples. So I did that factorization rather quickly. You know how to factor quadratics if you have to guess and check a little bit. Okay, so I am just going to assume that this is some number over 2x plus 9 plus some other number over x minus 5. Right? I am just assuming this is possible. If I multiply both sides by both factors, on the left I just get x, here I get a times x minus 5, and here I get b times 2x plus 9. Please write this initial step and make it perfectly clear what a gets paired with and what b gets paired with. You can choose which one goes first and what you call A and B. Sometimes when people are communicating with each other, it feels like they disagree. Oh, I got A equals 3 and I got A equals 4. But you actually had A as the name of different things. So make it crystal clear. Here in my example, A is the numerator that goes with 2x plus 9. B is the numerator that goes with x minus 5. And you can even give them different names. So now what we want is we want to figure out which combination of A and B make it so that this function, the function x, is the same as this function. And I'm going to show you two methods. You can decide which one you like the best. I feel like both will work pretty much all the time. I hesitate to say all the time. Be familiar with both, but pick the one you like and you should be fine. So one method, this is the one I typically prefer. I want to really think of these as functions. So I'm going to rearrange them. Both of these represent linear functions. Here I have just plain x. And then on the right, if I move things around, I will notice that my coefficient of x is a from here plus 2b. And then my constant would be negative 5a plus 9b. So if I rearrange things, I realize I have a linear function where the coefficient in front of x is a plus 2b, and the constant is minus 5a plus 9b. On the other hand, let's actually write this as x plus 0. Right? I want these to be the same function. They're linear. That means they're the same line. That means they must have the same slope and the same y-intercept. So essentially, the coefficient in front of x over here should be the same as the coefficient in front of x over here. Right? They are the same line. So if they are the same line, they have the same slope. And the y-intercept should be the same. If they're the same line, they have the same y-intercepts. The y-intercept here is 0. The y-intercept here is negative 5a plus 9b. And then we would just solve this algebra 1 style. I will multiply the top one by 5. And I'm just going to tell you, I picked this example somewhat randomly. There's no guarantee that the coefficients will be pretty, but we'll get them. Right? The answer is what the answer is. So if I multiply top and bottom by 5, I get 5 equals 5a plus 10b. So if I add these up, I get 5 equals 19b, b equals 5 over 19. Then I could plug into one of these equations. So I know 1 equals a plus 2b. So 19 over 19 equals a plus 10 over 19. So if I subtract, I have a equals 9 over 19. So this was how I obtained A and B by matching coefficients. This is my go-to method. It's probably not the faster one, but to me it feels a little more systematic. I'll show you the other method. We should get the same A and B, and then we'll finish the problem. Right? So you can reflect upon what you like best. Here is the other way you can do this that tends to be a little bit faster, but just to me it feels less systematic. It's certainly valid. So here's what we're going to recognize. We're going to recognize that these should be the same function. So if they're the same function, it means whatever I plug in for x, I get the same results. If I plug in x over equals 2 here, and I plug in x equals 2 here, they should be the same. If I plug in x equals negative 7 here, and I plug in x equals negative 7 here, those should be the same. So what you can do is you can plug in convenient values. Convenient meaning, are there values we could plug in that would allow us to solve for something really quickly? And the trick is, let's create zeros. So for example, if I plugged in x equals 5, I would have that 5 equals a times 5 minus 5 plus b times 10 plus 9, right? I plug that in knowing it would give me 0. So this gives me 5 equals b times 19, and we get b equals 5 over 19. That sounds familiar. Now, if I wanted to find a, I could look at this one and plug in something convenient. And maybe it doesn't feel quite as convenient. It's not quite as simple. But if I plugged in x equals negative 9 halves, I would have negative 9 halves equals a times negative 9 halves minus 5. I'm just going to create that common denominator already. Plus b times, right? And I pick that so I get 0. So I'm going to do another page here because I'm writing kind of big. So I would have negative 9 halves plus a times negative 19 halves, right? So, sorry, equals. This number equals this thing. So that would mean negative 19 halves times negative 2 over 19 equals a, which means a equals 9 over 19. And I hope that's what we got before. Yeah, right, so same numbers. And I'll just give you a warning. I picked this problem somewhat randomly. Often the problems that show up, someone has worked it out that you're going to get nicer coefficients, right? A lot of integers will show up, not these things. But it's still doable. So now let's remind ourselves why we cared about all of this. We were working under the assumption that this complicated rational function could be rewritten as something relatively simple plus something else relatively simple. And we have figured out what those values are. So let me just copy this whole thing. And let's resume the problem. Right? We had to pause for quite some time just to do some algebra. So what we can now say is this integral we were trying to do is actually the same as a over 2x plus 9 plus b over x minus 5. And I will double check that my value for a was 9/19 and my value for b was 5/19. When we have constant numerators and linear denominators, we can always do it with natural log. So what we'll have here is natural log of the absolute value of 2x plus 9. And then we would have 9 over 38. I need that extra 2 to cancel the chain rule. Plus natural log of absolute value of x minus 5. And the coefficient is just 5 over 19 plus c. It is not a particularly elegant looking answer, but it is the answer. So here is one for you to try. And again, I um, I can't remember actually if I set this up so that there were nice coefficients. What I will tell you, so just file this away, right? So promise is that usually on assessments, A and B will be easy. But again, this example, I think maybe I just wrote it down knowing that it's possible, not checking if they get easy ones. Right, so see how far you can get if you're watching this on your own. Hit pause and get as far as you can. So our denominator factors. And so what we're hoping is that I can write this as something over 2x plus something over x minus 3. I'll do my cross multiplication. Well, not really cross multiplication. Yeah, you could call it that. I'm multiplying by both factors of the denominators. And let's plug in convenient values. Let's do that method. It is faster. So if I plug in x equals 3, I get 11 equals 0, because I chose it as 3. And then that's b times 6. So it looks like b equals 11 over 6. If I plug in x equals 0, I get negative 1 equals a times 0 minus 3 plus 0. So that's negative 1 equals negative 3a. So it looks like a equals 1/3. Right, so that was relatively painless. They're not the simplest coefficients, but we got them pretty quickly. So what we know now is that this integral we're trying to do is actually a over 2x plus b over x minus 3. And it doesn't really matter how exotic those coefficients are for doing the calculus. So we have, you could write this one in a few different ways. I'm actually just going to pull out that 2 and imagine it's not in the denominator. You're going to get equivalent answers no matter how you do it. I'm going to imagine this was actually just 1/6 over x. So I'd have 1/6 natural log of the absolute value of x plus 11/6 natural log of x minus 3 plus c. If you did this another way, you might have had a 2x in there. And here's something I just want you to be aware of. Right? This seems not right, but the natural log of 2x plus c and the natural log of x plus c are actually the same. Because if we use the log rule, this is the natural log of 2 plus the natural log of x plus c. And so since this thing is a constant, it can get absorbed into the c and we just have a different constant. So sometimes when logarithms are involved, depending upon the choices you make, two people might have answers that appear to be different, but they're actually the same because of the c. That also happens with trig sometimes. People have answers that look very different, but it turns out that one is just more than the other by a constant, and some trig identity shows up. So, right, you've practiced this, you'll continue practicing for homework. Right? Once you sort of know this exists, it's not that hard to do it. It's just algebra. It's algebra you could have done in Algebra 1. It's just that we weren't really motivated back then. So I don't think it's particularly hard once you know this method exists and do it a few times. Now, we could add a few wrinkles. So what if our denominator is a perfect square? Right, so I will notice that what we have here is 3x plus 5 over quantity x minus 2 squared. Oh, I left out a dx here. Yikes. Did I leave that out in other ones? Oh, I hope not. So what wouldn't really make sense, I'm going to write something and then delete it, so don't copy. It doesn't really make sense to say, oh, I'm going to do a over x minus 2 plus b over x minus 2, right? Because at the end of the day, that's just one number over x minus 2. So if we have a perfect square, we need to do something a little more clever. And here's how it works. I am going to say that 3x plus 5 over x minus 2 squared is some constant a over x minus 2 plus some constant b over x minus 2 squared. You'll notice this is not the same as this because here it's just a constant. So that's the trick. So now I will eliminate the fractions by multiplying everything by the squared one. So if I multiply everything by x minus 2 squared, I get 3x plus 5 equals a times x minus 2, because one copy cancels and I still have one left, plus b. Here I'm going to use the matching coefficients technique. So I have 3x plus 5 equals ax, and then my constant is negative 2a plus b. So the coefficient in front of x must be the same. A is equal to 3. The constants must be the same. 5 is equal to negative 2a plus b. But we know that a is equal to 3. So 5 is negative 6 plus b, and that looks like b equals 11. I'm going to need to create another page here. I write kind of big when I do this. So we have created our partial fractions decomposition. Right? Actually, I can squeeze it in back here. So now, right, so this was just kind of my algebra on the side. Now I'm going back to the problem. So a was 3. This is 3 over x minus 2. And b was 11. This is 11 over x minus 2 squared. The first one we do with natural log. And the second one, right, we have u to the negative 2 power. So that's actually going to be negative 11 times this thing to the negative 1. Again, there's a chain rule extra 1, but we don't have to cancel it because it's 1. Right, so this one isn't log plus log. This one is log plus something that's more algebraic. Something I'm just going to remind you of, and I hinted at this already. When these show up on the AP, sometimes your answer won't be listed because maybe you got something like, oh, I got 2 natural log of x plus 3 minus 2 natural log of x minus 1. What you need to realize is you can use log rules to rewrite that. Hopefully you remember that subtracting logs with the same base is the same as the log of a quotient. Right, so maybe this is the answer that's listed. Plus c, plus c, plus c. Maybe they even use the rule that says a number in front is the same as a power inside. Right, these are all possible. In multiple choice, you really need to be aware that my answer isn't listed, but maybe it's the same as a listed answer because of some sort of way of rewriting things. Okay, so we saw a couple of examples where we had 2 different factors in the denominator. We saw an example where the denominator was a perfect square, but they were always proper. This method only works with proper rational functions. What if we have an improper rational function? That would be a case where the numerator has a degree same as or bigger than the denominator. And here is a fact that hopefully you saw in some version in pre-calc. Maybe it wasn't presented to you this way, but any improper rational function can always be written as some polynomial, right? And technically a constant all by itself is a kind of polynomial, plus some proper rational function. You can do this by long division, or sometimes you can just kind of figure it out by noticing simple enough patterns with easy numbers. So here, for example, I notice I have degree 3 over degree 2. You're not going to be able to do this directly with that first method. Because we had A and B, we were just solving for two things. It's not going to work. There's no way of setting this up so that we can somehow break it up into multiple fractions. It's algebraically impossible. So what we have to do is we actually have to break this up into something that's really easy, right? A polynomial. From an integral point of view, this is easy. And then for the proper part, we just learned this method of partial fractions. So we're being flexible. I'm rewriting this so that part of it is super duper easy and part of it is not that hard because I learned this trick. So I'll show you two ways of breaking this up. So the more intuitive way, hopefully when the numbers aren't that big, is we can just sort of rewrite that numerator in a way that looks convenient. So the idea is we want to create simplification. And I begin by looking at the biggest term. So I notice I have 5x cubed and x squared. I really want that to cancel down to a 5x. And it would cancel down to a 5x if I actually had 5x. Right, so we'll notice that this right here is just 5x. I could factor out the 5x here, x squared minus 1. Now, I don't have negative 5x. I actually have negative x. So here's what I'm going to do. This has been accounted for. And then negative 5x isn't actually there. But what if I add a 6x someplace else? Then negative 5x plus 6x. Oh, no, sorry, plus 4x. Sorry about that. Negative 5x plus 4x is the negative x I had, right? So I really wanted to see a negative 5x. But I know that's not my actual value, so I'm writing it as, here's a negative 5 I can see, here's a 4 over here, and they add up to negative 1. Now, what else do we have? We have this 2x squared. I have a 2x squared, and I would love to cancel that with the x squared below. And it would cancel nicely if I actually had 2x squared minus 2. 2x squared minus 2 over x squared minus 1 is just the number 2. Right? I want to see negative 2 here. But I know the value isn't actually negative 2, the value is 7. So let's add a 9 someplace else. Right? The things that I don't really want to see, I'm just putting on the side. So now we can notice this 2x squared is accounted for here, and then negative 2 plus 9 is 7. So I've actually accounted for everything. So what this means is the function that I am integrating is actually 5x, if I simplify this part. If I simplify this part, it's just 2. And then what I'm left with is 4x plus 9 over this factorable denominator. So I've broken this up in terms of really easy, and something that I can know I can do my partial fractions decomposition to. So we still have to do some algebra. Before we do that, another way of getting here, if you want to be a little more systematic, we can roll up our sleeves and officially do polynomial long division. I think you all learned this in pre-calc. X squared into 5x cubed goes 5x many times. 5x times that denominator is 5x cubed plus 0x squared minus 5x. If I subtract, here I get negative 2x squared. Here I get 4x, bring down the 7. Now it goes in negative 2 times. Negative 2 times my divisor is negative 2x squared plus 0x. Oh, I just miscopied, sorry. This should be a plus 2, so this should be a plus 2, so this should be a plus 2. So this should be a minus 2, and we're subtracting that. So we get a remainder of 4x plus 9. Right, so that squares with what we saw before. It goes in 5x plus 2 times cleanly, and then what's left over is 4x plus 9, which still has that denominator. All right, so now let's do our partial fraction decomposition. I'm going to assume that 4x plus 9 over this denominator is the same as a over x plus 1 plus b over x minus 1. Multiply by all those denominators, and I get 4x plus 9 equals a times x minus 1 plus b times x plus 1. If I plug in x equals 1, that's super convenient, and I get 4 plus 9 equals 0 plus b times 2. So 13 equals 2b, and b equals 13 halves. If I plug in x equals negative 1, I get negative 4 plus 9 equals a times negative 2 plus 0. So 5 equals negative 2a, and a equals negative 5 halves. So finally, we realize that the integral we're actually doing is 5x plus 2 plus negative 5 halves over x plus 1 plus 13 halves over x minus 1. This is where we kind of remember that our motto throughout chapter 7 is that we're not learning that these are fast, and we're not learning that these are easy. We're learning that these are possible. So many functions really can be integrated if we know a lot of tricks and are patient. So we have 5x squared, or 5 halves x squared, plus 2x. Here we would have negative 5 halves natural log of x plus 1, absolute value bars, plus 13 halves natural log of x minus 1, absolute value bars, plus c. Plus c. Not simple, not quick, but it is doable. Right? Theoretically, if you need to know an antiderivative for some rational function, you can get there using what we've seen, especially if the denominator factors. If the denominator does not factor cleanly, you can try to mimic this with irrational numbers. It's a total mess, but theoretically it works. If the denominator has more than 2 factors, you can do something similar by breaking it up into 3 fractions. We're not going to go into that. That's where I feel like we cross the line from what is interesting to what is tedious. But basically, almost all rational functions can be integrated. Right? I think all of them, if you can figure out the factorizations. Yes, if you can figure out the factorizations, you can always do them. I think that sounds right. But it may not be easy at all. Okay, that's the end of this video.